In this video, we're going to be discussing compound inequalities. Like compound sentences and compound words, compound just means the union of two or more parts, and this we're going to be doing compound inequalities, both of the or type and the and type. So that's what goes in these boxes here. We're going to join these by the word and or, and we want to make sure we logically understand what that means. This example is an and inequality, and it says two things. It says x is less than 6 and x is greater than 3. So that's how you read that. And because it says those two things within one statement, that is a compound inequality. One thing we need to remember is that the word and means both. So in order to be considered a solution to a compound and inequality, the value of x would have to satisfy both of those two parameters, like x is less than 6 and greater than 3. So numbers like 4 would be a solution there. Remember, there are only two integer solutions, 4 and 5, for that scenario, but there are an infinite amount of numbers that would satisfy that compound inequality. The word or just means one or the other is necessary in order to be considered a solution. And so on the next page, we're going to just kind of quickly practice this with some silly examples that I have. The number 4 is even. Yes, it is. And positive. Yes, it is. So you got to be thinking and is where both need to be true. Or is where at least one needs to be true. So I'm going to underline the things that are true, and then we'll determine using the word and, or, like in those cases there, and determine whether the statement itself is, or the example in the statement is a true statement. So the number 4 is even. Yes, it is. It's positive. Yes, it is. And because we have both of them that are true, and the word was yes, both were there, this is a yes. Dogs have fur. Yes, they do. Dogs have horns. No, they don't. This was an and. Both of them were necessary, so that is a no. Today is a blue day or a white day. Well, as I'm recording this, today happens to be a white day. It is not a blue day. But the word or indicates that only one of them needs to be true, and therefore this is a yes. Indianapolis is a city. Yes, it is. It's a capital. Yes, it is. The word was and. They were both there. So, yes. Sharks have teeth. Yes, they do. Since the word is or, I could go ahead and say yes, because it doesn't matter whether this is true or not. However, sharks do have fins, so it's true. That one's just doubly good. It's an overachiever. Sharks have teeth. Yes. Sharks have fins. Yes. The word is and. That's a yes. Cows eat cats? No. Cows eat grass? Yes. The word was and. We need both. We only had one. That's a no. Horses eat mountain lions? No. Or grain? They do eat grain. The word was or. We only need one in that situation. So that's a yes. And now a little more mathematical example here. The number 7 is less than 9. That's true. Greater than 12? Is 7 greater than 12? No. But the word was or. So only one of those is necessary. So this is good enough. 7 would be considered a solution to that compound inequality there. The number -4 is less than 0. That is true. Greater than 2? No. The word was and, so we need both of them in order to write yes. Since we didn't have both of them, that is a no. Hopefully that just gets you thinking about the and the or and really what we're doing here. Now we can look at some examples. This is an or compound inequality, and you can tell because, well, it says or. And all you're going to do is you're going to solve this separately. So take the -6 plus 12x less than or equal to 114, and we're going to solve. So I would add 6 to both sides. You're going to get 12x is less than or equal to 120. Then you are going to get x by itself by getting rid of the multiplication using a division of 12. So you end up with x is less than or equal to 10. So what numbers are we talking about? Well, here's 10. The numbers less than 10 would be there. And since it says equal to, we're saying that 10 itself would work in this inequality because 10 is not less than 10, but 10 is equal to 10. And so that is a solution there. So all the numbers that have been shown on this graph will satisfy this inequality. But remember, or means, it's not just those numbers. Any of the ones that satisfy this inequality is fine too, because we don't have to satisfy both of these inequalities. One or the other is fine. We know that these numbers would work for the first one. Let's see about the second set of numbers. To solve this one, you would just add 5, and you'll get x is greater than 12. So not only will the numbers less than 10 or equal to 10 work, but the ones that are greater than 12 will work. And so my final answer, you would write like this. You'd put them in the or format here with the word or between them. And this would be your answer. You're describing the set of numbers that would satisfy this compound inequality. These numbers will satisfy this one. These numbers will satisfy this one. And so that's all the numbers that would do that. And then we draw a picture to help us give a visual of those numbers. And clearly you can see that 11 doesn't work. Actually, 12 doesn't work because it's not filled in. And then there are an infinite amount of numbers here that don't work, but they're all greater than 10 and or up to 12. So, but these numbers work and these numbers work because the word or, a number from either set, is fine. Let's look at a couple more examples of the or type. We have x over 2 is greater than 2. I'm going to multiply by 2 on both sides to get x by itself. So any number, that's how I like to read it, any number greater than 4. So I go to 4, any number greater than 4 is fine. Or we have this. I'm going to divide by 4 to get x by itself. You get x is less than or equal to 2, or any number less than 2 or equal to 2. So any of those numbers that are indicated here would work for this compound inequality. And let's do this one. Subtract 5. You will get n is greater than negative 5. Or subtract 5 on this one, and you'll get n is less than negative 6. So any number greater than negative 5, well, here's negative 5, any number greater than negative 5, or any number less than negative 6. So that is what those numbers, those are the numbers that would satisfy this compound inequality. Those are all of them described in mathematical notation right here, and then shown in this graph right here. So let's go to this idea of and. And, remember, is going to be us finding the numbers that satisfy both of these. You're not good enough if you just satisfy this one or if you just satisfy this one. So we want to find out the numbers that are the solutions to the first inequality. Which I would do by subtracting 2. Then I'm going to get the x by itself, which means that the negative 12 is needing to leave. We do that by division. If you'll recall, we divide When we divide by a negative with an inequality, we're going to have to flip the sign around, and we are going to get x is less than -1. I'm actually going to move this up, give myself a little more space. So let's go ahead and solve the next one before I explain how we're going to do this. I rewrote on the last one, so I guess I'll do it here. First step would be to add 9. We are going to get 6x is greater than, and this is a -24. Then to get x by itself, we would get rid of the 6. I'm trying to keep consistent with my colors here. And we're going to get x is greater than -4. So these are the two requirements that are going to be defining our numbers here. So in the green, I'm going to do this with a highlighter that's lighter in color. It says any number less than -1. So here's all the numbers less than -1. And the blue says any number greater than -4. So here's -4. I know that's pretty faint. Hopefully you can see that. It's not my answer just yet, but we're looking for the numbers that not only are in the green section, meaning they satisfy the first inequality, but they're also in the blue section, which satisfies my second inequality. Because remember, because of the word and, you need both. So where is that? Well, you're going to be looking for, and that's what this little blank is, you're trying to look for the overlap of these two graphs. So it goes from -4 up to -1. Neither of those numbers are included, -4 or -1. And you're saying then, we're going to rewrite this in a different way. Just like it was on that first example, they didn't have the word and in there. We're going to write this as -4, which is less than my x values, which those x values are less than -1. So what two things does it say? It says x is less than -1, which is what that part says, and x is greater than -4, which is what that part says. And we've combined it, and this is the notation that we would prefer for an and inequality. Notice it doesn't say the word and. The or ones will always say or. So let's continue here. Try this one. I'm not going to rewrite it this time. 11a is greater than -88. Then we would divide by 11, and you will get a is greater than -8. So that's one set of numbers that will satisfy the first inequality, but we have to pay attention to the second one. On this one, you're going to subtract 9 in order to find those answers, and you'll get a is less than or equal to -4. So there are my two parameters. I am going to use my highlighters again. The green one is greater than -8. So here's -8, and we're going greater. And then -4 and equal to and less than. So we're looking for the overlap. Well, that would be from here to here. So -8 up to -4. The -4 is included, but the -8 is not. And then looking at the graph, it's probably easier to write this style inequality once you have it graphed as the overlap. But it's basically just saying the lowest limit is -8. You can't go down any further. And it doesn't actually get to -8 because -8 is not included. And then you have x. I'm sorry, the variable here was a. And you have a. And a is less than or equal to -4. And so this would be your answer, and this would be your graph. Maybe a little different at first. Let's just take a look at a couple more. In this situation, you have a compound inequality. It's an and the variable is in the middle section. What we do is, when the variable is only in the middle section, I would prefer to just isolate the variable in that middle section, and it'll look a lot like the final answer of what we did in the previous two examples. So if I wanted p to be the only thing in here, I'd need to get rid of the -6. I would add 6, but I have to do this not only to the left side, but I'm going to do it to the right side as well, because we are basically solving two inequalities at the same time. And when it's set up like this, they will be the same steps. So we read this like a book. We're going to get 3 is less than nothing plus p, which is p less than or equal to 4. And this is your answer. And you're going from 4 down to 3. You're going to fill in the 4. And you want the numbers less than 4, which is this way. And you want the numbers greater than 3, which is this way. And that is the entire graph. Let's look at the next one. We still have the variable in the center section. I'm going to need to subtract 3 first. You'll get 36 is less than, 3's go away, 9m is less than or equal to 108. Now I need to get the m by itself, which means I need to get rid of the 9. And I would do that by division. Divide by 9, divide by 9, divide by 9. You will get 4 is less than m, which is less than or equal to 12. Once again, we have our answer the way we would like it, and we go all the way up to 12, and we got to be above 4. So in between there are the answers, and then because 12 actually is a solution, we want to fill that in. So those are the numbers from 4 to 12, including 12, excluding 4, that would satisfy this compound inequality. Let's look at another one that's a little different, a little more difficult for us. We are going to have to separate these into two inequalities because we're seeing the variable not only in the middle, but on the left and the right. And so we are going to write this as k plus 18 is less than the expression 18 plus 9k. And the second inequality will be 18 plus 9k is less than or equal to 3 plus 6k. So we're going to solve this one. You'll notice we have variables on both sides, and from previous equations and inequalities, we need to eliminate one of the variable terms. So I'm going to get rid of k by subtracting k. Now remember, that's a 1k minus a 1k now, and I'm going to subtract 1k over here. So after doing that, my inequality will read 18 less than 18 plus 8k. My next step is to get the variable term by itself. So I want to get rid of this 18, and I will do that by subtracting 18. I do it to both sides to preserve the relationship. We get 0 is less than 8k. Last step is to get the k by itself, which means I need to get rid of the 8. So I'm going to divide by 8 and then read it like a book, and I will get 0 is less than k. I would rather that say k first. So if 0 is less than k, I'm going to read that as k is greater than 0. And that is going to be my first set of numbers. Anything greater than 0 is halfway there. Let's look at the green inequality here. We do have variables on opposite sides. I'm going to eliminate one of these variable terms. I'm going to eliminate the 6k. So I'm going to subtract 6k from both sides, and you will get 18 plus 3k less than or equal to 3, and the 6k's cancel out. Then I'm going to get the variable term by itself, which means I need to get rid of the 18. I'm going to subtract 18, and I'm going to end up with 0. 3k is less than or equal to negative 15. Now I'm going to get k by itself. Not consistent there. Now I'm going to get k by itself. And so I need to get rid of the 3. So I divide by 3. You'll get k is less than or equal to negative 5. So that's the second stipulation for the numbers that need to satisfy this inequality. Let's look at our graphing. We say k is greater than 0. Well, any number greater than 0 would look like this section. That is really faint, so I'm going to do that again, another color. And the second requirement is that k is less than or equal to negative 5. So negative 5 works, so I'll fill that in. But if we want the numbers less than that, then we go this way. And remember, we're looking for numbers that are in both sections. And since there is no overlap, there is no solution here. So for an and inequality, with no overlap is a no solution. There is no number. Okay, let's go to this last page where we have 2 more examples. One of the types that doesn't say and one of the types that does say and. And then I'm going to add on just a couple little notes about special situations that could show up. So since our variable is only in the middle, we can isolate that just by subtracting 5 on each side. You'll get negative 20 less than or equal to negative 4p less than or equal to negative 8. Now my variable's in the middle still, but it has a coefficient, and we need to get rid of that coefficient. I gotta get rid of that negative 4. So I'm going to divide by that coefficient on all 3 parts, and it happens to be negative. So we got to do something here where we flip this inequality symbol around. Mathematically, that has to happen in order to keep the statement true. And then you'll get those numbers. 5 is greater than or equal to p, which is greater than or equal to 2. So p is greater than 2. So here's 2. P, the answers are greater than 2, but those p values are also less than 5. Both of these have the inequality symbol, so since that is both of these have the equal to, so I fill that one in, and this one has the equal to, so I fill that one in. Those are these are the I'm getting jumbled. These are the answers. This is the graph for those answers. And lastly, we have a compound and inequality with just separate inequalities already. We're going to solve them. First thing is I want to get the variable term. I see that it's on both sides. I want to get one of those to go away. I'm going to get rid of the n by subtracting n. So now I have 1 plus 14n is less than or equal to 15. Now I'm going to get the variable term by itself. So get rid of this 1 by subtracting 1. So now we have 14n is less than or equal to 14. And then we want to get rid of the coefficient. Now when we're getting rid of the coefficient, which is the 14, we're going to divide because that's a multiplication. So now we have n is less than or equal to 1. And let's do the second one. I'll do it more primarily in green. We have variables on both sides. I need to eliminate one of those. Subtracting the 6n would get rid of the 6n. I'm going to do that to both sides. Now we have negative 6 is less than n plus 17. And we're going to get n by itself. So I'm going to get rid of the 17. So we subtract 17. And we're going to get negative 23 is less than n. In other words, I would like to write this with n on the left side. We're going to n is greater than negative 23. And the word is and. So we want the overlap of those two inequalities. So let's look. N is less than or equal to 1. I'm going to keep going. And n is greater than negative 23. Negative 23 is about right here. Okay, these do overlap. You can see there's a section where both. So we would go from negative 23 all the way up to 1, and we would fill in at the 1. So now looking at the black part of my graph, how I would write this as an inequality like we see over here would be from negative 23, which is less than my numbers n, excuse me, and less than or equal to 1. So the last thing I want to talk about, and this is not on your notes, but it's going to be helpful to you in case you run into these situations, are some compound inequalities. You should know how to solve them at this point, but then graphing them can be a little tricky. So if I had something like x is greater than 5 and x is greater than 7, that's one of my examples I'm going to talk about. If I had x is less than 4 or x is less than or equal to negative 2. Let's just do these really quickly. So hopefully you'll be able to get your inequalities simplified down to just something like this. And then we have a 5, we have a 7, and we have the inequalities x is greater than 5 and x is greater than 7. And what this does is it kind of breaks this into 3 sections. Okay, so in section, I'm going to label them with letters. In section A, B, and C. Remember, we're looking for the numbers that say that the numbers that satisfy both of these inequalities. So if you look in section A, the numbers here don't have anything graphed to indicate that they're basically 0 for 2. In B, you have numbers that are 1 out of 2. They got one of the inequalities satisfied, but not both of them. So the real answers are in section C. So instead of this inequality saying x is greater than 5 and x is greater than 7, we only want to describe these numbers because those are the ones that are the solutions to the compound. And so final answer would just say x is greater than 7. That's the real only requirement necessary if these are the two inequalities. Similarly, if we're doing an or, let's say we had 4 and negative 2, like I've given the example of, x is less than 4. So here's 4. Anything less than 4 works for this guy. Anything less than negative 2 or equal to negative 2 works for this guy. Now you see those 3 sections, and I can call them A, B, and C again. Do the numbers from A satisfy at least, remember, since it says or, we only need at least one. Do the numbers from section A satisfy at least one of these two inequalities? And the answer to that is yes. Do the numbers from section B satisfy at least one of these? The answer to this is yes. Do the answers in or the numbers in section C satisfy at least one of these? That answer is no. So where are my solutions? How would you describe them? Well, all of these numbers work, and all of these numbers work, and it will work forever this way. So the final answer here is that anything less than 4 is a solution. And so when you go to graph it, that's actually all you would do. You would just go to 4, go less than. You wouldn't need to do anything else other than that. Hopefully that helps you understand some of those situations that might arise. If you have any questions, please let me know.